Hi, everybody. Thanks so much for having me. I have a lot of ground to cover because Professor Davis asked me to cover the entire geologic history of the Appalachian Mountains, why the Appalachian Mountains exist, and why that could be a setting for Demon Copperhead. So I'm going to move through a discussion of the story of Virginia's different geologic provinces. And these are different parts of the state that have unique rocks and therefore a unique geologic story. And I think of them as sort of like the chapters in a book. So I'm going to read these book chapters to you, translating them as I go. I am fluent in the language of rock, and my job today is to translate rock into English for you guys to understand. So I've got an outline of my talk here. This is my outline. I'm going to build the Appalachian Mountains in 10 steps. And the good news here is that many of these steps are fairly repetitive. They represent similar geologic processes, such as mountain building, like steps 1 and 6 and 8 and 4, and tectonic rifting, like steps 2 and 9, and then times of tectonic calm, what we call passive margin conditions, like steps 3 and 7 and 5 and 10. All right, so here's the North American continent, of which Virginia is a part and the Appalachian Mountains are a part. This is color-coded to show the age of the rocks. The oldest rocks are in the middle of the continent, and then younger rocks have been tacked on to the margins of the continent through time. This has built out the continent over geologic time into what we find today. And so we're going to look at evidence of the first tacking on of material to the North American continent in the oldest rocks of Virginia, and these are found in the Blue Ridge geologic province. They include granite, which is an igneous rock, used to be magma deep underground, and a rock called granite gneiss, which used to be a granite, but then it got squeezed, and it's got these alignments of its minerals that reflect its squeezing. These rocks are something that you may have seen if you've ever been to Shenandoah National Park or hiked Old Rag Mountain. This is a picture of Old Rag's granite. And these are rocks that formed during an ancient episode of mountain building. And in geology, we refer to episodes of mountain building as orogenies. You're going to hear a lot about orogenies in today's talk. These orogenies basically are times when continents smash into one another and raise up land masses. But rocks form as a result of that smash up, including these granites. So we date these back to the Grenville orogeny. And when I see those granites, I think of something like a modern day orogeny like the Himalayas. All right, so the Appalachians don't look like the Himalayas anymore, but the Himalayas are young. And if you give them enough time, the mountains will erode away and they'll look more subdued in their landscape like the Appalachians do. So this Grenville orogeny, this ancient continental smash-up, built an ancient supercontinent called Rodinia. Most people are probably familiar with the more recent supercontinent called Pangaea, but Virginia's geologic history goes much further back in time than Pangaea. It goes all the way back to this approximately 1 billion year old supercontinent called Rodinia. And there were mountain belts all over the world's continental crust at that time, stretching from Scandinavia to Australia and India and Madagascar and a zillion other places as well. So we think this was a time of great supercontinent collision. But this Rodinia supercontinent didn't last. Like all good things in life, it came to an end. And that is our second step in building the Appalachian Mountains, which is ripping apart Rodinia. As the crust stretched, cracks opened up, and then magma welled up along those cracks. And in some cases, that magma erupted on the surface. And in other places, like in these photographs, it just sealed the crack shut with a dark seam of rock that we call a dike. We think that these dikes were feeding surface lava flows, so we go ahead and we call them feeder dikes. So one of the big themes for today is this eruption of lava, and Virginia has quite a lot of lava, which is, of course, the origin of our state motto. So if you look for a modern day analog for the breakup of Rodinia, you can find it in East Africa today. That's a place where the African continent is ripping itself apart. And one of the consequences of ripping itself apart is these massive eruptions of a rock called basalt. Basalt is an iron-rich lava that flows out over the surface in a very fluid way. It's not very viscous, and it fills in the low spots in the landscape. We have these ancient lavas in Shenandoah National Park where they show beautiful cooling columns like in the right two pictures, and in fact underneath the campus where I'm speaking to you now. All right, we have these same lava flows there. So these lava flows record the breakup of Rodinia and the opening of a brand new ocean basin called the Iapetus Ocean. If you've never heard of the Iapetus Ocean, that's okay. You didn't miss that day in geography class. The Iapetus Ocean no longer exists. It's been destroyed, all right? We call it the Iapetus Ocean because the modern ocean in that same place is the Atlantic Ocean, and the Atlantic Ocean is named for the Greek titan Atlas. Atlas's father was a Greek titan too. His name was Iapetus. So we named the ocean that came before the Atlantic Ocean for the Greek titan who came before Atlas. Hence, Iapetus Ocean. So this Iapetus Ocean opens up, and then Virginia basically is on the shore of that ocean, and there are various sediments being deposited in different places along that shoreline. And over time, sea level rises, and it brings all these different oceanic sediments over Virginia, and so they build up in a vertical stack through time. By the time we get to the top of that stack, things have really calmed down, and we have these beautiful beach sands that are very rich in the mineral quartz. And in many places in Shenandoah National Park, you can see these quartz sandstones with these weird little soda straw tubes running through them. Those are trace fossils called scolithos, and we think they represent ancient worm burrows. So when I see this sandstone here with those worm burrows, I imagine a really calm beach, no mountains anywhere nearby, no volcanoes erupting, and just lots of quartz sand building up, and then living in that quartz sand, some little wormies digging their holes. All right, so we've covered the first of our 10 steps in building the Appalachian Mountains. Now we're going to move on to the next sequence of steps, basically transitioning from these calm water conditions into the various Appalachian mountain building episodes. So things are calm. The beach sand even gets submerged underneath water, shallow waters where there are microbial mounds photosynthesizing in the shallow sea. The waves are agitating these gentle little grains of calcite called ooids, and these things are building up layer upon layer like a little Target department store logo or a hailstone or a jawbreaker candy. They have these little layers, and that indicates they're being gently washed by the waves in an environment that would be a lot like the modern day Bahamas. So if you went back in time to like 500 million years ago, this is what Virginia looks like. It no longer looks Himalayan, instead it looks Bahamanian. All right, so that's the situation as we enter the Paleozoic era of geologic time. You can see in this paleogeographic map, this imagining of what the land would have looked like back then, that the western half of Virginia is there, but it's under a shallow sea. And then out in the Iapetus Ocean, we have a chain of volcanic islands, all right? We call these volcanic island arcs, and they're produced through this process called subduction. So subduction takes old oceanic crust and it shoves it down into Earth's mantle, and that allows blocks of crust up on the surface to come together and smash into one another. So we're going to have a series of smash-ups that build the Appalachian Mountains. The first of those is when this volcanic island chain runs into North America. The second is when a microcontinent, a small continent, so think like Madagascar, runs into North America. And then finally, the Iapetus Ocean closes for good and Africa runs into North America. And that's the thing that makes the supercontinent Pangaea. Pangaea itself breaks apart through time, and then that opens up the Atlantic Ocean. So we're going to get there. All right. So first stage of Appalachian mountain building is the collision of the volcanic islands with the ancestral North American continent. All right. In the ocean between the volcanic islands and North America, a dirty sandstone was deposited. This dirty sandstone is called graywacky, which is a fun name to say. All right. It's gray in color, and as you can see, it's totally wacky. All right. So how do graywackies form? They're deposited in the deep ocean by underwater landslides called turbidity currents. And here's a picture of one that I made in my lab back when I worked at the Annandale campus of NOVA. It's a density current. It's a slurry of sand and mud and water, and it hugs the bottom as it flows out into deep water. As it slows down, it deposits its sediment, but the big pieces drop out first because they're the heaviest, and the lighter weight pieces stay suspended a little bit longer, so they get deposited last. And this produces a characteristic bed that is coarse-grained at the bottom and fine-grained at the top. It's called a graded bed. And you can see these graded beds in these ancient Greywacke sandstones at places like Great Falls Park in McLean. All right, that's the rocks that underlie Great Falls. In some places, the Greywacke has big chunks of other rocks in it, and so there had to be some mechanism to mix bigger chunks in with these deep water sandstones. And one way to do that is when you're scraping those Greywacke sandstones off the subducted oceanic crust, you also scrape off some pieces of the oceanic crust and mix that in as well. It's sort of a big tectonic blender that jostles all these different rock types into positions next to one another. So then the islands and North America get closer and closer, and the poor little Greywackes get caught in between, and then they all squish up into an episode of mountain building. This is the Taconian orogeny, named after the Taconic Mountains in upstate New York. It happened around 450 million years ago, 460 million years ago. Our graded beds of ocean Greywacke got all folded up. These are photographs, well, the left one is one I took on the Billy Goat Trail near Potomac, Maryland. And then the right one shows garnets, which are a metamorphic mineral that grew in these Greywackes when they got all hot and bothered due to this collision. Another thing that happened when they got really hot is they started to melt, and that melting generates a magma that is granitic in composition. Essentially, granites are made out of the easiest to melt minerals. So when you have a bunch of different starting minerals and you partially melt it, you extract a magma that is a granite. And we can actually see the rocks that were leaking out this granite. They were essentially sweating it out in the Potomac Billy Goat Trail area. Another place where we can see the resulting granites is at our many granite quarries in the region. This is an example of a granite quarry near Occoquan. All that white colored rock there is granite that was produced through partial melting during this first phase of Appalachian mountain building. Then, after the Taconian orogeny was over, the Taconian Mountains weathered away, and then we go back to passive margin conditions, where we're depositing nice clean sandstones and limestones again. So I've got a picture here of a fossil in a limestone to represent this gap between orogenies. But it's time for another orogeny now. The second phase of Appalachian mountain building is the Acadian orogeny. These are my brand new license plates, by the way. So one orogeny follows another. And this Acadian orogeny is named for Acadia National Park up in Maine. And that's a photograph of Acadia there on the right. But this is the collision between North America and an ancient microcontinent. And that microcontinent was kind of long and skinny, and it smashed first up in the area around New England, and then it kind of was like a zipper closing shut, moving to the south. And in our neck of the woods, this mountain building episode really got going around 360 million years ago. If you go up to New England, the dates are a little bit older, but basically all of New England is the roots of these Acadian mountains. And the rocks there have these metamorphic minerals that suggest that they got really hot, or maybe medium hot, or maybe not so hot. So we can actually map out the different kinds of metamorphic minerals, and that can tell us basically where the highest mountains used to be, mountains that have long since been erased from the topography of the Earth's surface. The other thing that the Acadian mountains did is they shed off a lot of sediment. Sticking all that rock up high into the sky produces a lot of gravel and sand and mud. And that gravel and sand and mud goes downhill and it ends up accumulating somewhere else. So the somewhere else is the Valley and Ridge province of Virginia and adjacent Appalachian states. And there we've got this tremendous stack of sedimentary layers. And these layers basically toggle back and forth between passive conditions where there is no mountain building going on. And so those are going to be marked by things like nice clean quartz sandstones and limestones. And then in the lower part of this diagram here, we've got these two episodes of mountain building, the Taconian orogeny and the Acadian orogeny, marked by a real dirtying of the sedimentary rock package. So basically you start getting a lot of gravel and a lot of sand and a lot of clay, and it basically makes a muddier picture, literally, all right? So that's what the stack of sedimentary layers in the valley and ridge looks like, except it doesn't, because it got all folded up during yet another episode of mountain building, yet another orogeny. It's just one orogeny after another to build the Appalachian Mountains. So this final orogeny is called the Alleghanian orogeny, and it represents the collision between ancestral Africa and ancestral North America. This is the collision that basically takes all those nice flat sedimentary layers and crumples them up and produces the young Appalachian Mountains. This assembles the second supercontinent that Virginia was lucky enough to be part of, and that's called Pangaea. And most people, when they start thinking about plate tectonics, they start thinking about the breakup of Pangaea. But Virginia records how Pangaea got put together too, and the supercontinent that came before it. So if you look at this map here, you could have walked from Nova into Morocco at that time, all right, which is pretty convenient, but you would have had to cross Appalachian scale or Himalayan scale mountains in order to do it. So here is some more paleogeography, all right, some more maps showing this collision. There's the last vestiges of the Iapetus Ocean there. Then those oceanic crust rocks get subducted, and that brings Africa into direct contact with North America. That raises up these young, mighty Appalachian Mountains and completes the assembly of the supercontinent Pangaea. All right. So once again, Virginia goes into Himalayan mode. All right. And we shove all these rocks up high into the air. They get eroded. They generate lots and lots of sediment. And again, that sediment goes downhill and ends up somewhere else. And in the case of the young Appalachian Mountains, it looks like a lot of that sediment went out to the coast of North America, which is the West Coast. And we have rocks like in places like Arizona that seem to record giant continental scale rivers like the Mississippi draining the young Appalachian Mountains and taking its dirt, its sand and mud out to places like the petrified forest. So the petrified forest in Arizona is an amazing place to see petrified tree logs, but the sediment that buried those trees came from the Appalachian Mountains. We have the minerals to prove it. So what actually happened during the Alleghanian orogeny to the rocks of Virginia? Well, to a first approximation, they got seriously messed up, all right? So they got folded. And if you think about a rock as being something that you can fold, you got to think like, okay, that's got to take place very slowly, or you got to get that rock really warm in order to get it to deform in that way. But we have all these beautiful folds of the rock layers up and down throughout the Appalachians. In Pennsylvania, they're differentially weathered, so the low-lying areas are underlain by limestones and shales. And then where you've got quartz-rich rocks, they hold up these mountain ridges that are not good for farming, and so they leave them covered with forests. So those are the green lines that are snaking back and forth across this aerial photograph. Here's a view of a fold that some of you may have seen out on Interstate 68 in western Maryland. This is Sidling Hill, and it's a fold that basically was caused by Africa running into North America. Here's another one. One of my favorite roads in our region is Corridor H in West Virginia that connects Wardensville, West Virginia to Davis, West Virginia. Martha, you should go to Davis, West Virginia sometime. And it goes through all these spectacular folded outcrops like this one here. These folds are really important for the world economy because it was in folds of the Appalachian Mountain Belt that the world's very first oil well was sunk. So folds that go up in the middle, called anticlines, tend to serve as traps that concentrate oil. And so you can then dig an oil well into the crest of that anticline and pump out the oil and sell it to people and make a lot of money. All right, so this is an important place for the world that we live in now. But Demon Copperhead does not take place in the Valley and Ridge province. It takes place largely in the Allegany Plateau. And the boundary between those is right in Lee County in southwestern Virginia. This is looking at the boundary between the Valley and Ridge on the right, or the east, the southeast, and the Alleghany Plateau on the left, which is to say to the west. The really orange colored stuff that you see down in the lower left along the bottom, that's the Dolly Sods Plateau and the Canaan Valley, which is a nice place to go skiing. So this is the Devil's Bathtub, and this is eroded into these Alleghany Plateau sedimentary rocks. They're just like those of the Valley and Ridge, except they haven't been folded. So they're still flat lying. Kind of think like the Grand Canyon, these sort of horizontal layers of rock. So this is where one of the culminating scenes of the novel takes place. And that Devil's Bathtub is right there. You can see it right on the lip of the Alleghany Plateau, right on the edge of that physiographic province. I used an app called Rocked to look into the geology of the site. And this is a geologic map, so the different colors represent different rock units. And there in the rock unit of the Devil's Bathtub is called the Lee Formation, and that's named for Lee County. And you can see that it says it consists of quartz arenite, which is a way of saying a quartz sandstone, conglomerate, sandstone, shale, siltstone, and coal. So I wanted to show you some pictures of what these rocks look like. These are photographs that I took at Dolly Sods up in the Alleghany Plateau further north in West Virginia. But on the left is a bunch of gravel, quartz pebbles that have been cemented together into a rock we call conglomerate. And on the right is some sandstone. And in many places there, the sandstone has impressions of plants in it, ancient plants, all right? Plants that are, 300 million years old. And in some places, you actually have the carbon that those plants pulled out of the atmosphere hundreds of millions of years ago, preserved as coal. And of course, coal is why people went to Lee County, Virginia in the first place, to mine that coal, to combust it, to power the economy. So basically reversing ancient photosynthesis for the modern industrial age. Another thing I noticed in looking at photographs online of the Devil's Hole area is that some of the rock layers there are tilted. So if you see here, you've got flat-lying layers, but then within those flat-lying layers, there are a series of tilted layers. Let's see if I did this right. Yeah, good. So those are called crossbeds, and those reflect an ancient current, probably an ancient river that was transporting this sand out of the young Appalachian Mountains and into this site where the sand was accumulating. So if any of you ever make it on a field trip down to this area, I hope you'll keep an eye out for those ancient current indicators. Okay, wow, we've been cruising through geologic time. We've done great. We've covered 8 of our 10 easy steps in building the Appalachian Mountains, which means we just have 2 to go. All right, another episode of supercontinent rifting, and then a return to passive margin conditions like we see in modern day Virginia. So rifting first. We break up the supercontinent Pangaea and we open up the Atlantic Ocean. Again, our analog would be modern day East Africa, where this is playing out in real time today. We have these ancient rift valleys that run up and down the East Coast. There is a big one outside of Newark, New Jersey, another one that runs through Hartford, Connecticut. Gettysburg, where the Battle of Gettysburg was fought, is in another one of these ancient rift valleys. And here in Virginia, we've got a whole bunch of them. The biggest one is the Culpeper Basin, named for Culpeper, which is on the route from Charlottesville up to like Haymarket. The Culpeper Basin is a Triassic-aged rift valley. It is bounded by faults on either side, and that dropped down a block of rock in the middle. That created a low spot in the landscape into which sediment poured and lava erupted. And so if you want to orient yourself to this diagram, the right side of it would be like Reston, and the left side of it would be Leesburg. And if you've ever flown out of Dulles Airport, that's smack dab in the middle of the Culpeper Basin. What do the rocks of the Culpeper Basin look like? There's a variety, but at the edges, they tend to be pretty big pieces of sediment, gravel, in other words. So this is an example of the Leesburg conglomerate. As you head further towards the middle of the basin, you get into sandstones. There's one particular sandstone that's got a lot of feldspar in it called an arkose. That's a very common one to find up there. And we call that sandstone by the name the Seneca Red Sandstone. It was quarried extensively in the early days of Washington, D.C. for use in building the infrastructure of the C&O Canal and also the Smithsonian Castle down on the National Mall. And in places, it has dinosaur footprints in it. So these are Triassic age dinosaurs that were stomping around in the mud of Virginia and leaving behind their fingerprints for us to see. Or not their fingerprints, their footprints. As far as igneous rocks go, there's a rock called diabase that also intruded into the Culpeper Basin, and this is quarried extensively for use in like road gravel and landscaping and stuff like that. If you ever fly into or out of Dulles Airport, get a window seat and look out, you'll see these giant holes in the ground. That's where they're pulling out this diabase. Okay, so the young Appalachian Mountains start eroding away at this point. We erode them down further and further, but not quite as far as we could go. We could have the landscape be completely flat. So mountain belts get less mountainous through time, but again, we can read the rocks and figure out where the mountains used to be. With the Appalachians, it looks like they actually did get eroded pretty much completely flat by around 100 million years ago, by the Cretaceous. And then sometime after that, they got kind of etched out again. So the land got uplifted and the rivers cut down into the landscape and gave us the landscape that we have today. But one thing that's really striking about the Appalachian Mountains is if you ever go to like Skyline Drive and you look off to the west, you'll see all these ridges of mountains going off to the west, but they're all about the same elevation. And that's a reflection of that ancient landscape. So the final thing that happens to build the Appalachian Mountains and give us the modern world that we have today is we deposit these sediments on the coastal plain. And this is our final episode of passive margin sedimentation. Basically, everything to the east of what we call the fall line or the fall zone is the Atlantic coastal plain. And these coastal plain rocks are very easily eroded. So where rivers flow across them, there are no rapids, there are no waterfalls. And that's really different from the harder rocks of Virginia's Piedmont region, where you do get rapids and you do get waterfalls. So if you're a European colonist sailing up the Potomac River or the Rappahannock River or the James River, you basically stop sailing your boat where your boat starts running into rocks. And so all the major cities of the East Coast line up on this major geologic boundary called the Fall Zone. If you climb to the tops of the highest hills in our region, you will find some Cretaceous-aged gravel sitting on top of those hills. So these are around 100 million year old river gravels, and they're no longer at the bottom of a river. They're now sitting on top of hills like Mount St. Alban in DC or Tyson's Corner. And these basically represent that switch from eroding away the first version of the Appalachian Mountains and then starting to deposit the layers of the coastal plain. On top of those gravels, we find other layers as well, all of them loose, not really cemented into solid rock, but in some cases they're able to support cliffs, like at Calvert Cliffs in Maryland. But if you look closely at the sediment there, it's mostly fossils. It's mostly, ancient scallop shells and snail shells and shark teeth and whale bones and things like that. Some of the layers are muddy, some of the layers are sandy, but all of them have that in common, that they're not very well stuck together. Speaking of fossils, both the state fossil of Virginia and the state fossil of Maryland come from the coastal plain. Virginia's state fossil is this beautiful scallop called Chesapeake jeffersonius. It's named after the Chesapeake Bay. Pecten is Latin for scallop, and Jeffersonius pays tribute to a guy that you may have heard of, a local boy here in Albemarle County, and he lived over on the hill that's just visible outside my window here, Thomas Jefferson. Thomas Jefferson, by the way, Martha and I know this, he went to William & Mary, but his kids couldn't get into William & Mary, so he had to found another school, the University of Virginia. All right, can't all be winners. Maryland state fossil is a snail. It's called Ecphora gardneri, a very beautiful snail, and that's all I'll say about that. Last thing I want to mention is that at the bottom of the Chesapeake Bay is a secret. And that secret is the largest meteorite impact structure in the United States of America. It's at the very bottom of the Chesapeake Bay, and it's called the Chesapeake Bay Impact Structure. It was discovered first through dredging of seafloor sediments off the coast of New Jersey, and there they found some telltale signatures of a giant meteorite impact, including little glass droplets called tektites, and a particular variety of quartz called shocked quartz that you can only produce if you apply a lot of pressure very quickly to a quartz grain and then release it just as quickly. They looked at fossils that were present in those same sediments, and they realized that this meteorite impact must have taken place 35 million years ago. So then they started looking around for a crater, and by drilling cores down through a couple of sites on the Delmarva Peninsula, they found jumbled up rock called breccia that marked the spot of the impact. And then they imaged it using seismic energy, basically setting off TNT and watching the shock waves go down through the sediments. And they revealed this giant sombrero-shaped structure at the bottom of the bay. So here's a little cross-sectional view showing the Piedmont rocks. These are these Iapetus ocean rocks that got tacked on to North America at the very bottom. And then they're overlain by gravels like 100 million years ago up to 35 million years ago. And then you had the impact, which gouged into all of that. And then since then, in the subsequent 35 million years, we've deposited new layers on the coastal plain. And some of those layers have actually sunk down a bit as the jumbled up pieces, the breccia, compacts. And that creates a low spot in the landscape where we have the modern Chesapeake Bay. So we wouldn't have the Chesapeake Bay if it weren't for this giant meteorite impact 35 million years ago. So here's what we've covered. We've covered 1 billion years of geologic history. We've built mountains and supercontinents. We've broken them up and made new ocean basins. We've had times of tectonic calm, and we even had a meteorite impact in there as well. So that is how you build the Appalachian Mountains in 10 easy steps. I'll be happy to take your questions.